This learning module discusses the material in section 3.2 about Galileo. The learning goals are to be able to explain Galileo's observations and how they disprove the cosmology of the day, and explain why Galileo is considered the father of modern science. Galileo's observations challenged the Aristotelian theory of motion. There's some excellent resources online and as well a folder in the learning module. Hans Lippershey is a Dutch-German spectacle maker who is commonly credited with the invention of the telescope. That said, Galileo was the first person to take that telescope and make astronomical observations with it. He observed that the moon has mountains, valleys, and craters, that the sun has imperfections and it rotates, Jupiter has moons, and Venus has phases. All of these were in direct contradiction to the general belief that the heavens were constant and immutable, part of the Renaissance belief that Aristotle's view of the world, cosmology, had a prime mover, and that prime mover was God, and the outermost spheres were unchanging heaven. Observations of the moon showed mountains and craters. His observation of the sun showed that it had blemishes, sunspots. It was not perfect. Those sunspots changed over time. There was motion to them. From the motion and the observation over the course of several days, one could ascertain that the sun was rotating. All of these contradicted Aristotle's beliefs. He looked at Jupiter and saw 4 bright planets he originally thought were stars, but he observed them over time and found that they orbited Jupiter. So he found something that was orbiting something other than the center of the universe, which people thought at the time was Earth. He saw the phases of Venus, and the phases of the Venus could not be explained by the Ptolemaic system. See, if you had phases of Venus, and you had the planet going around some other center other than Earth, other than the sun, then it would wax and wane in 2 cycles instead of 1. So the phases of Venus are impossible to explain in the Earth-centered model of a solar system. He actually observed Neptune, though he didn't recognize what it was. We've only been able to figure out that he saw Neptune in retrospect from studying his journals. He observed Saturn and didn't have a really good resolution with his telescope, so it looked like 3 spheres together instead of the sphere with rings around it. He observed Saturn's rings at a time when it would look like 3 separate things. In Galileo's experiments, he showed that a body in motion stays in motion unless acted upon. This also challenged Aristotelian views that the natural state of an object was to be at rest. In a tract written in 1576, Giuseppe Moletti, Galileo's predecessor in the chair of mathematics at the University of Padua, reported that bodies of the same material but different weight, as well as bodies of the same volume but different material, dropped from a height, arrived at Earth on the same time. And he published De Modo challenging Aristotle's motion. Galileo. In 1600 AD, Giordano Bruno was burned at the stake in Rome. He was a Dominican friar, philosopher, mathematician, poet, and astrologer. It is widely held today that Bruno was executed for teaching about a Copernican solar system, and that stars had planets, and those planets had life, and that the universe was full of life. Galileo's motions experiments can be roughly divided into 3 or 4. There was the pendulum motion, which led to better timekeeping, and then he had several experiments that gave him his law of free fall and his laws of inertia, Weights from the Tower of Pisa dropped, the inclined plane, and projectile motion. All of these disprove the Aristotelian laws of motion. So he was sitting in a cathedral and watching this cathedral chandelier swing back and forth, and he noticed that it had a constant period even when moving at different angles. He actually counted these with his heartbeat. So he counted the number of oscillations within a specified time, which he used his heartbeat to get, and he examined a variety of pendulums later outside in his laboratory and claimed that the period is each totally independent of the size of the arc through which it passes. So he discovered a crucial property that makes pendulums useful as timekeepers, and that is isochronism. It's that a period of a pendulum is approximately independent of the amplitude or width of the swing. He also found that this period is independent of the mass of the bob and proportional to the square root of the length of the pendulum. He first employed the free swing pendulums as simple timing applications. His friend Ch03 invented a device that measured a patient's pulse length of the pendulum by the length of the pendulum, and Galileo in 1641 actually conceived of and dictated to his son Vincenzo a design for a pendulum clock. Vincenzo began the construction but was unable to complete it when he died in 1649. The pendulum was the first harmonic oscillator used by man. In one of the most famous stories about Galileo is that he dropped balls of different masses from the Leaning Tower of Pisa to demonstrate that their time of descent was independent of their mass, excluding the limiting effect of air resistance. And this was contrary to what Aristotle had taught, that heavy objects fall faster than lighter ones in direct proportional to their weight. So he was able to show this law of free fall, that all free-falling objects fall with the same acceleration towards Earth's surface in the absence of air resistance. This experiment is so important that David Scott of Apollo 15 performed it on the moon with a hammer and feather.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct in his findings.
Superb.
Galileo used an inclined plane with 5 small bells and a pendulum to demonstrate his law of falling bodies. Using his law of isochronism, the pendulum serves as a stopwatch for timing the duration of the ball's motion. A small ball was released from the top end of the plane at the same time as the pendulum is swung. At each successive complete oscillation of the pendulum, the ball strikes one of the small bells placed along the inclined plane at increasing distances, arranged in the sequence of odd numbers. This ingenious design not only enables us to measure the increase in distances traveled by a body in natural fall in successive and equal time intervals starting from the position of rest, but it also provides auditory confirmation of the constant acceleration of the ball during its fall. Galileo used this inclined plane to get better measurements. Since it slows down the ball's motion, it enables the mathematical modeling of the experimental observations, and it also corrects for some of the effects of air resistance. Galileo showed that the distance of descent always varies closely to the square of the time, and that the final velocity of the ball depended on how high the ball was, not directly to the plane's incline angle. He could explain the kinematic motion, that is just motion as it is, but not explain the underlying cause. In projectile motion, Galileo showed that you could decouple or separate the horizontal motion from the vertical motion. So he set up these experiments where he shot balls using the inclined planes to give him the initial velocity, and then having a little ramp, and the projectile would then go into a free flight. He showed that the horizontal and the vertical motions were separate from each other. So you had the horizontal path, which was gravity free, going at a constant velocity, and the vertical path accelerating as the free fall. These experiments he had showed that motion appearance had a frame of reference. It's called the Galilean frame of reference. So Galileo used a pendulum to demonstrate the law of inertia and that heavy and light bodies fall at the same rate. He also discovered the mathematical laws governing the length of the string and the period of motion and the amplitude of the swing. He used the inclined plane and its rate of acceleration to show that to slow down the motion of falling objects enough to accurately measure how their speed increased. And projectile motion he used to these inclined planes to control the speeds and heights of projectiles in order to discover mathematical properties of their paths, in particular to be able to separate those. So where Aristotle thought from free fall that heavy objects fell faster than light ones, since they had more earth than air, fire, or water in them, Galileo saw that all objects fall at the same rate. Regarding inertia, Aristotle thought that an object in natural motion moved to its natural place and stopped, and that to keep it moving in a violent motion, it required energy. Whereas Galileo formulated the law of inertia, that an object in motion tends to stay in motion. Our senses supported Aristotle. This is our everyday experience because we forget that friction works against things. But Galileo's experiments aimed at purifying the senses by isolating only the effects of weight from all the other causes involved, such as air resistance, friction, and buoyancy. So as an experimentalist, he told us how to isolate the one or two variables that we were interested in studying and minimize or reduce what was going on. In 1623, Galileo published the Assayer. This is generally considered to be one of the most pioneering works of the scientific method. The central idea is that nature is to be understood with mathematical tools rather than those of scholastic philosophy, and that differs from Aristotle's beliefs, which were still held and followed. Ironically, it started as an attack on a Jesuit astronomer, Orazio Grassi, who in 1618 hypothesized that comet orbits Earth. Galileo ridiculed him, saying that comets were a play of light artifact, and Galileo was wrong. The comets orbit, they just orbit the sun, not the Earth. Here's a quote from the Assayer. "The universe cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. Without these, one wonders about a dark labyrinth. He stressed that quantification was the route to true knowledge and physical reality. He abandoned the Aristotelian stress on the qualitative aspects of bodies. Galileo argued that secondary qualities like color and taste were just names given by people to the impressions that bodies made on their senses. Science should concern itself only with the size, shape, and relative motion of objects. Galileo's mechanical philosophy undermined key aspects of traditional Aristotelianism. Aristotle distinguished matter and form. A table, for example, was made of wood, that's matter, but was only a table because of its substantial form, its tableness. Galileo's theory completely ignored form. Aristotle's philosophy was teleological. It considered final causes. The final cause of the acorn was an oak tree. The final cause of the acorn falling to the earth was its purpose, like that of all bodies, of moving the earth. Galileo's theory posited that matter in motion blindly responded to universal physical laws of motion, not taking them into consideration the form. And pendulum motion, he was able to show, was a period independent of amplitudes. That supported his laws of motion. Galileo showed that the Aristotelian view of a perfect immutable heaven was incorrect. The moon was not a perfect sphere, it had mountains. The moons of Jupiter did not orbit the Earth, they orbited Jupiter. The heliocentric hypothesis couldn't be proven with 1600s technology. Galileo inspired the church to review Copernicus's book in 1615, but he was cautioned not to hold or defend these ideas. Galileo boldly took up the challenge of proving it, presenting his arguments in the dialogue concerning the two chief world systems in 1630. He took a real risk, especially considering how they had executed Bruno. It is a myth that Galileo proved the heliocentric model was correct. In his dialogue, his arguments were factually incorrect. Galileo rejected Kepler's laws on philosophical notion that orbits would be perfect circles. Galileo proposed that tides were proof that Earth moved. He rejected Kepler's suggestion that the moon caused tides. His book argued that tides prove heliocentric hypothesis. He thought the combination of Earth's rotation and orbital motion produces a faster motion at the point of the Earth farthest from the Sun and slower closest to the Sun. He argued that the speed produces sloshing of oceans, creating tides, and that tides are seen from Earth reference frame, but change of the speed was only with respect to the Sun. High and low tide cycle every 12 hours, so his arguments produced only one tide per day, and that didn't make sense. So here the empiricist was finding that experimental observation didn't fit his theory, and yet he held on to it. Galileo published his heliocentric views in Dialogo sopra I due massimi sistemi del mondo. In this piece, which was set as a play, was not unlike scientists of the day to have more creative ways of expressing their scientific theories. Simplicio was the defender of the earth-centered views, and he used arguments made by classical Greek philosophers and the Pope, but is made to sound comically stupid. Censors felt that it insulted the Pope, and Galileo was convicted of heresy and placed under house arrest. In 1979, the Catholic Church re-examined Galileo's case and found that Galileo should not have been condemned. In 1992, Pope John II endorsed those findings. Galileo Galilei was an Italian physicist, astronomer, and philosopher who is closely associated with the scientific revolution. His achievements include improvements to the telescope, a bunch of astronomical observations that revolutionized our understanding of the universe, the first law of motion, the second law of motion, and effective support for the Copernican theory, although he wasn't able to show that it was any better than the geocentric models of the day. He has been referred to as the father of modern astronomy, the father of modern physics, the father of science. His experimental work is widely considered contemporary to the writings of Francis Bacon in establishing the modern scientific method. Galileo's career coincided with that of Johann Kepler. The work of Galileo is considered to be a significant break from that of Aristotle, and in addition, his conflict with the Roman Catholic Church is taken as a major early example of conflict of authority and freedom of thought, particularly with science and Western society. And that's all coming from Wikipedia and elsewhere. So, in conclusion, Galileo's discoveries came from his being the first to use the telescope for astronomy. He discovered the Galilean moons around Jupiter, and that our moon has craters and mountains, and that the phases of Venus don't work with the geocentric system. His discoveries were controversial because they contradicted widely held geocentric view of the universe and an immutable heaven. He experimented with falling and moving objects and crafted a model of motion. He said that an object in motion will continue moving along a straight line with a constant speed until an unbalanced force acts upon it. That is Galileo's law of motion. As a father of science, he gave us two major steps above it. In addition to empiricism, that is, making observations, he viewed the world as a machine consisting of matter in motion, and the mathematical laws that govern its motion are what we were to figure out. He also came up with this notion of reductionism, that qualities of complex objects can be explained completely by an examination of the basic forms of the components that make them up, and that the scientific laws that can govern them. He also gave us this idea that we have the primary or inherent properties of an object, its size, shape, number, or speed, and that those are the things that we should measure and model, and that secondary properties are a response to that object. Galileo saw that all sensible quantities, such as color, sound, warmth, taste, and smell, are really only in the mind.